Heyo there, what do you hear, what do you say? Synchron here, and today I'd like to talk about trying to understand quantum entanglement. Here's a quick overview, but before we get into that, I'd really appreciate if you like and subscribe, comment, let me know your thoughts and what other topics I should look at in future videos. So first of all, there's the introduction, what is quantum entanglement? Then there is basic quantum mechanics, where we talk about fundamental concepts like wave-particle duality and superposition. There is visualizing entanglement, how experiments help us understand it. There is the mathematical representation, there are the philosophical implications, there are the applications and future prospects, and finally there's the conclusion and the references and the further reading. So what is quantum entanglement? Quantum entanglement is one of the strangest and most fascinating discoveries in science. It describes a situation where two particles, tiny building blocks of the universe, become deeply connected. This means that no matter how far apart they are, if you measure something about one, you instantly know something about the other. Even if one particle is on Earth and the other one is on the moon, or even across the galaxy, they remain linked in a way that seems to defy common sense. Why this breaks the sort of classical rules of physics is that in everyday life, objects interact in predictable ways. If you move a book on a table, nothing happens to a book in another room. In classical physics, the physics of everyday objects, things influence each other through forces such as magnetism, gravity, and so on. And those forces take time to travel. Albert Einstein's theory of relativity says that nothing can send information faster than the speed of light. If this is true, then two objects separated by a great distance shouldn't be able to just affect each other instantly. Yet quantum entanglement seems to do just that, creating a connection that appears to work outside of time, space, and time on the face of it. And this challenges two very important ideas. Locality, this is the idea that things can only be affected by their immediate surroundings, and however, entanglement suggests that distances don't really matter. Realism, we assume that objects have definite properties even when we're not looking at them, but in quantum mechanics, properties only become quote-unquote real when they are measured. Now, obviously, there's more to say about this particular topic, and if you'd like me to sort of delve into it, please let me know. But suffice to say, we'll just leave it there for now. Einstein, along with physicists Boris Podolsky and Nathan Rosen, found this idea troubling. In 1935, they proposed what is now called the EPR paradox, arguing that in quantum physics must be complete. If entanglement were real, it would mean two particles can influence each other instantly, which Einstein dismissed as spooky action at distance. Einstein believed there must be some hidden variable, some unseen factors that would explain the connection without breaking the speed limit of light. However, there have been stronger and stronger evidence to suggest that entanglement is a real phenomenon. In the 1960s, physicist John Bell came up with a way to test whether quantum entanglement was real or whether hidden variables might explain it. His idea, called Bell's theorem, gave scientists a way to check whether the universe followed Einstein's rules or quantum mechanical's strange predictions. In the 1980s, Elaine Aspect and other researchers performed experiments that proved Einstein was wrong. Entanglement is a real, and no hidden variables can explain it. The results confirm that when one entangled particle is measured, its partner instantly takes on a corresponding state, no matter how far apart they are. Going over basic quantum mechanics describes how the tiniest parts of the universe, like electrons and photons, behave. But unlike everyday objects, these tiny particles don't follow the usual rules of physics. Instead, they exist in strange and counterintuitive ways, behaving as both waves and particles, and even existing multiple states at once. And this concept is encapsulated by the concept of wave-particle duality. In our everyday world, things are either particles, such as grains of sand, or waves, such as ripples in water. But in the quantum world, things don't fit neatly into one of these categories. Particles like electrons and photons can behave like tiny balls in some situations, but like spread out waves in others. For example, if we fire a beam of electrons through two slits in a barrier, they don't just create two straight lines on a screen behind them, like tiny bullets would. Instead, they form an interference pattern, just like waves in water, suggesting that each electron behaves like a wave passing through both slits at the same time. But when we place a detector to see which slit each electron goes through, the wave-like behavior disappears, and the electron acts like a tiny particle again. This means that simply observing the phenomena changes the behavior. With respect to the measurement and wave function collapse, this is very, very peculiar. If a particle exists in multiple states at once, how does it sort of settle on one, right? How does it know to, quote unquote? The answer is measurement. What we observe or interact with a given quantum system, its wave function, the sort of mathematical description of all the possible states, collapses into a single definite state. This means that the quantum objects don't have definite properties until they are measured. Before you check, an electron's location is spread out in a wave, but once you measure it, the wave collapses and the electron appears at a single spot. And this is encapsulated by superposition. Unlike objects in our daily lives, quantum particles don't have definite properties until they are measured. Instead, they exist in a superposition, meaning they're in multiple states at the same time. Imagine you flip a coin. In classical physics, the coin is either heads or tails, even if we haven't looked at it. But in quantum mechanics, before we check, the coins coexist in a sort of superposition, where they are sort of both heads and tails at the same time. Now, obviously, this analogy only goes so far. There are certain nuances, and it's not really very accurate, but it sort of gives you a sort of rough idea as to how strange this phenomena is. Only when we look at it does it, quote unquote, choose one outcome. A famous thought experiment by physicist Schrödinger illustrates this idea. He imagined a cat in a box with a quantum device that could either release poison or not, based on a random quantum event. Until someone opens the box, the cat is not just alive or dead, it exists in a superposition of being both alive and dead. Here we go on to the experiment and visualization section. And I think it's really sort of useful to sort of try to visually sort of capture in your mind what this is supposed to look like. So imagine you have these electron spin experiments where you have the given setup where you have a pair of entangled electrons and they are generated and they are sent in opposite direction to two distant detectors. Each detector randomly chooses an axis, X, Y, or Z, to measure the electron spin, recording it as either up or down. The results being that when you measure the spin of one electron, this instantly fixes the spin of the other, even across vast distances. The outcome consistently violates Bell's inequality, eliminating the possibility of hidden variables influencing the results, with the conclusion being that these experiments provide clear evidence that entanglement is a genuine quantum phenomena, unexplainable by classical physics. There are photon polarization studies, where the setup in this case being a specialized crystal producing entangled photons, which are directed to two detectors positioned far apart. Each detector independently measures the photon's polarization, the orientation of their light waves using randomly selected settings, with the result being that the polarization of the photon show a strong correlation that exceeds what classical physics can account for. Like the electron experiments, these results violate Bell's inequality, reinforcing the reality of entanglement, with the conclusion being that photon-based studies offer very compelling sort of visual proof that quantum entanglement persists over large distances, solidifying its place in physics. With respect to loophole-free Bell tests, modern experiments time and time again sort of confirm quantum entanglement. Detection, they measure all the particle pairs avoiding the biases. Locality, the detectors are frankly just too distant for light speed signal. Choice, quantum random settings rule out hidden correlations, with the result of all this being that Bell's inequalities are consistently violated, disproving local hidden variables. With the key insight being that entanglement, proven with electrons, photons, or more, show that quantum mechanics is fundamentally non-local. Now, this drives various innovations such as quantum computing and cryptography and teleportation, not the kind that you're thinking about, but we'll get into that later. There is, of course, the mathematical representation. This is physics, after all. So this equation represents a maximally entangled state of two quantum particles, A and B. The state of one particle is not independent. Measuring one immediately determines the state of the other. And there's a sort of anti-correlation. If particle A is measured in state 0, particle B will always be measured in state 1 and vice versa. And before measurement, both particles exist in a superposition of these states. As you can see the equation, this equation has sort of various notations, and foremost among them, the first one is psi, right? This represents the state quantum vector, and it's commonly used to denote a quantum state, and the angle are part of the Dirac notation, a standard way of representing quantum states. The 1 over root 2, this is a normalization factor. In quantum mechanics, state vectors must be normalized so that the sum of the square of the amplitudes equals 1, ensuring that the total probability of finding the system in any possible state is 1. In this case, it ensures that the state is properly normalized. This sort of part, the part afterwards, describes the superposition of two possible states for two qubits labeled A and B. So sort of in summary, the equation describes the quantum states where two qubits A and B are entangled. The state is a superposition of two possibilities, either qubit A is in state 0 and qubit B is in state 1, or qubit A is in state 1 and qubit B is in state 0, with a specific phase relationship between them. And there are the philosophical implications. What does it mean for reality? Quantum entanglement sort of challenges a lot of fundamental assumptions about how the universe works, and it does raise a whole host of sort of philosophical questions about locality, realism, and the nature of reality itself. And obviously, probably the one that it attacks the most directly is this idea of locality. Objects are only influenced by their surroundings. There is sort of no faster-than-light effects. Now, this is very unusual. Like, just on the face of it, just when you sort of think and reflect about our sort of understanding of the world, locality is probably one of the most common, pervasive principles that we sort of adhere to day to day. And yet it just seems to not be true at the sort of quantum mechanical level. And it seems to also, this is a bit more, controversial, but it seems to challenge realism, the sort of idea that physical properties exist independently of measurement. And with respect to quantum reality more broadly, entangled particles affect each other instantly, right? This is pretty much shown beyond any sort of reasonable doubt, and this violates locality, with measurement determining the given properties, implying reality isn't really the sort of predefined as we initially sort of thought it would. The conclusion obviously being that at least one classical assumption must be false, right? You can't. And moving on to sort of hidden variables, Einstein believed that quantum mechanics was incomplete, arguing for hidden variables, unknown factors that would restore determinism to its rightful place, so to speak. Bell's theorem, that was talked about in the 1960s, provided tests for hidden variables, and experimental results from the 1980s to now confirms entanglement and rules out local hidden variables, with the conclusion being that reality is, at least in some important respect, fundamentally non-local or probabilistic. Now, the thing that should be noted is that when it comes to quantum mechanics and quantum entanglement, there are various competing interpretations, right? All of them are sort of mathematically consistent with with the given data, right? And that's the thing, is that usually the way to sort of adjudicate between them is usually going to be down to some theoretical virtue or due to some other thing within that particular interpretation that sort of seems fruitful to that particular physicist, right? But anyway, I'm getting ahead of myself. I'm going to be giving a very, very sort of short and sort of a little bit facile and reductionistic account of the Copenhagen and many worlds interpretation, because we just sort of have to sort of be constrained. But keep in mind, there's always more to say. There's always more nuance, and I just want to state at the outset. So with respect to the Copenhagen interpretation, this was advocated most famously by Niels Bohr, and this is the idea that reality exists in a superposition until measured. The measurement collapses the wave function into a single outcome, with the implication being that reality sort of depends on observation in some sense. And the many worlds interpretation, this is a deterministic interpretation of quantum mechanics, is the view that there is no collapse, in fact, right? All possible outcomes occur in parallel universes in some respect. The measurement causes branching rather than randomness, with the implication being that sort of infinite realities sort of coexist with each other in some sense. What are the applications and the future prospects for this? So first of all, there is quantum computing. This uses entangled qubits, to perform complex calculations exponentially faster than classical computers. Unlike classical bits, zeros and ones, qubits exist in superposition, allowing parallel processing, with an example being that Shor's algorithm could break traditional encryption methods using quantum speedups, with the impact being enormous, right? It enables breakthroughs in AI, drug discovery, optimization problems, and so forth. Another one might be quantum cryptography. Quantum key distribution, or QKD for short, ensures secure communication using entangled particles. Any attempt to intercept the transmission disturbs the entanglement, immediately revealing eavesdropping, with the example being a BB84 protocol used to develop ultra-secure encryption methods, with the impact being that it provides unbreakable security for finance, defense, and sensitive communication. By the way, guys, if there's anything that you think I could improve on or I need to sort of understand more, please let me know in the comments. Thirdly, we're dealing with quantum teleportation, where this refers to transferring quantum information instantaneously between distant locations using entanglement. It does not teleport matter. That's what I was sort of talking about earlier. It only teleports quantum states. However, even then, it still has applications. Teleporting the quantum state of a photon across large distances could be very helpful. It could lay the foundation for quantum networks and maybe even a quantum internet. So the key takeaways being that quantum computing can revolutionize problem solving with entangled qubits, quantum cryptography could provide unhackable security or near enough, and quantum teleportation enables secure instant data transfer. So in conclusion, why does all of this matter? Quantum entanglement is more than just a bizarre phenomenon. It challenges our fundamental understanding of reality and unlocks groundbreaking technologies in many ways. It can lead to a sort of new understanding of reality. It defies classical assumptions about locality and realism. It demonstrates that particles remain linked even beyond space and time, perhaps. Although that is a bit more controversial, like everything is in some respect. It raises profound philosophical questions about observation and reality. And secondly, of course, is that it could lead to a foundation for revolutionary technology. like we discussed earlier, quantum computing, cryptography, teleportation, and future applications such as quantum networks, sensors, and AI advancements could all change our understanding of reality and help change the world drastically. So finally, there's just the references and further learning. This is just like a list of resources that I found quite helpful, and I think that you might find helpful in some important respects as well. Just whatever sort of tickles your fancy, just give it a look through. And yeah, I'll be uploading videos every Sunday from now on. If you have any particular topics that you would really like me to talk about, please let me know. And yeah, this is Synchron signing off.